Okay, this is introduction to the Arduino, given for the Atlanta Hobby Robotics Club by Ted Summers in December of 2012. Topics I'll be covering are powering the Arduino, connecting devices to the Arduino, installing the Integrated Development Environment, the IED, and an introduction to coding in the IED, and using libraries. Powering an Arduino. Okay, here's our standard Arduino, the Uno, which is pretty much the standard. This is the power jack. This is a 2.1 millimeter jack. Just uses a standard wall wart. And this is the power header. And this is, I'm zooming in now on the power header, and we're looking now at the VN pin. And this pin can take anywhere from 6 to 12 volts, 6 to 20 volts under ideal conditions. And that's not going to be found on a robot. On a robot, you're really going to want to shoot for 9.5 to 12 volts. Closer to 12 is better, because on a robot, if you go below 9.5 volts, you're really running into the danger of browning out your microcontroller. If you go over 12 volts, you're in danger of overheating the power converter on the Arduino. Okay, the 5 volt pin is an out in this condition. If we're powering it from VN, then the 5 volt is an out. Oh, and putting power to VN is exactly the same as using that 2.1 millimeter barrel connector. Okay, and the 3.3 volt pin is also an out. Now the 5 volt pin has a maximum of 200 milliamps of current coming out of it. If you use any more than that, you are endangering the power supply on your Arduino. And the 3.3 has much less current available. You can only put a maximum of 50 milliamps out of the 3.3 out pin. Now the Arduino Mega, which is a different version of the Arduino than the Uno, it's a much bigger, beefier Arduino. It has 4 5 volt pins, and each one of those pins can support 200 milliamps, so you get a maximum of 800 milliamps if you use all 4 pins, 5 volt pins on a Mega. Okay, now if you want to power the Arduino through the 5 volt pin, now before, when we were talking about it here, when we were using the VN, the 5 volt is an out. But you can use the 5 volt pin as an in to power it. But in this case, your 5 volt must be regulated. In other words, that 5 volts has got to be very, very steady. You don't want any ripple in it. You don't want it to go down. You don't want it to go up. You don't want any variation at all. You want a very, very constant, very steady 5 volts, which means it's coming from some sort of regulator. Like a good example of that would be if you have a motor controller that has a battery eliminator circuit, a 5 volt battery eliminator circuit. That's a 5 volt out, and it's a very regulated out. So that would be a good way to put your batteries to your motor controller, and then use the motor controller to give a regulated 5 volt out to your Arduino. In this case, you would still be able to use the 3.3 volt out as an out only. You cannot use the 3.3 as an in, and you still have a 50 milliamp maximum output on that 3.3 volt pin. Now, some Arduinos have the name Pro in them. They're an Arduino that you might see an Arduino Pro or a Pro Arduino. they only have this 5-volt pin. They do not have the VN pin. They don't have an onboard regulator. And that's why they're pros, because you have to know what you're doing. You have to understand what it takes to give a regulated 5-volt power to this microcontroller. And one thing you've got to remember about this 5-volt pin is this is powering the microcontroller almost directly. There's very little filtering here. So if you do overvolt, you could easily damage the microcontroller. Okay, connecting devices to a Arduino. Okay, this group of pins here is the digital header. It is both input and output, depending on how you configure these pins in software. And here's your typical device that you might want to give a digital in to an Arduino. It's an ultrasonic ping detector that will measure a distance using sound. It sends out a sound pulse, and then it hears the reflection of the sound pulse, and it measures the time difference. Well, you actually measure the time difference using the Arduino, and that gives you the time of flight for that sound, which gives you the distance. And this picture is actually a picture I got right off of Parallax's website. And there's something wrong with this, and I see this quite a bit. When you connect an external device to your Arduino like this, when you're getting a 5-volt out to power this sensor, you want to put a 0.1 microfarad capacitor, ceramic, across those pins. This keeps any noise from the sensor from going back into your microcontroller. And remember, that circuit is powering the microchip on your microcontroller. So any sort of ripple, for example, when that ping sensor generates that sound pulse, that could create a small brownout on your 5-volt rail, and that could cause a brownout for your chip. So definitely, whenever you connect anything, you want to isolate it. And there's many articles out there about how to properly isolate components from one another. And I would definitely recommend you Google isolating electrical components from an Arduino, or just in general. A lot of good information about that, and there's lots to learn. Okay, we're going to look at connecting analog devices. This is the analog in. And that's all you use these pins for. Remember, these pins were both in and out for digital. But for analog in, that's all these pins do. They do not do analog out. But they can also function as digital pins if you configure them that way. Most of the pins can be reconfigured as digital pins, but these are your analog pins. And here's an analog device that you would typically connect to an Arduino. A Sharp IR sensor. It does the same thing the ping sensor does, but it uses infrared light instead of sound. It's a little more accurate, and it's a little faster. You can get more data from this, more readings per second with this device. And if you'll note, and this is another diagram I got off the internet showing you how to connect it, and just like the ping sensor diagram that I got off the internet, it's missing something. These pins, where you're getting the power from, really need a 0.1 microfarad capacitor on them to isolate the Sharp IR sensor from the Arduino. And that is particularly important with Sharp IR. That LED, it has a very bright LED that is pulsing, that is turning on and off rapidly, and it creates a tremendous amount of noise on the 5-volt rail, and I have had these sensors reset my microcontroller because of that. And if you read the manufacturing specs for the Sharp IR sensor, it actually tells you to put a capacitor on that line. Okay, connecting devices. Okay, to the digital pins. In or out. Analog is hidden inside. Now we covered analog in. What about analog out? Believe it or not, that's on the digital pins. They're here. You see the little squiggly line next to the number on each of these pins. That denotes that that pin can be used as an analog out, in addition to being used as digital input and output. And that's all configured in software. In your setup routine, when you write your program, you configure how you want to use that pin. So these are digital in, they're digital out, and they're analog out. But there's more. These digital pins down here are also your I2C lines. These pins down here are your serial lines. So that's a lot of double duty. I mean, look at pin number 3. That's a digital in, a digital out, an analog out, and an I2C line. So a lot is going on. Oh, and when I say analog out, it's not true analog, it's a simulated analog called pulse modulated bandwidth. Which basically means that you're sending actually a square wave out, and you're modulating how much time you spend up versus how much time you spend down. It's kind of complicated how it works, but for most devices we'll see it as an analog signal. Look up PWM if you want to know more. Notice how your pin use affects how many of each pin type you have. In other words, if you need 13 digital pins, you won't have anything left over for analog. You won't have anything left over for serial or I2C. You really want to take this into account when you're buying a microcontroller, because it might say it has so many of this kind of pin and so many of that kind of pin, but it might not make it really apparent that some of these pins overlap and you can't use them at the same time. You can't have 13 digital pins and all the analog pins on this microcontroller. Once you've dedicated a pin as a digital in, you can't also use it as an analog out. Once you've used it as a one sort of purpose, you're stuck with that. Okay, destroying your Arduino. Okay, never do any of these. Connect IO, VN, 5 volt, or the 3.3 volt pins directly to ground. In other words, the wire you just run a wire straight from one of those pins to a ground pin. If you do that, you'll get too much current. You'll go past the current limit, and you will overheat the component and you'll let the smoke out. Of course, if you put a current limiting resistor in there, you're fine. Never connect an I/O pin directly to each other. For example, if one pin is high and the other pin is low, you've effectively connected a high to a ground. And again, you're going to soak too much current, and you're going to destroy the pins or destroy the microcontroller altogether. You never overvolt any of the I/O pins or the 5 volt or 3.3 volt pins. If you do, you will destroy the pin or the entire microcontroller. Reverse polarity on the VN, 5 volt or 3.3 volt pins. Believe it or not, the Arduino is not reverse voltage protected, so be very careful that you don't reverse them. And like I already said, we have a 200 milliamp current limit for the 5 volt rail. Make sure you never go over that. Never draw more than 40 milliamps from any output pin, in other words the digital out or the analog out. You never want to go over 40. 20 is recommended, so you really don't want to go over 20. Now, in researching all of these never do's, I came across this Arduino clone called the Rugged Duino. which is at ruggedcircuits.com, and it actually protects you from every single one of these. It has reverse voltage protection, it has overvoltage protection, and it does all this with fuses and with voltage protection circuitry. Diodes. Okay, installing the IED. First you want to download the IED. The IED is, again, the Integrated Development Environment. That's where you write all your code. It's the text editor, basically. And you're going to download that from Arduino CC, which is a great website. Great website. Copy the file structure. It's going to be in like a zip file, and you're going to want to unzip that and put the file structure in your programs directory. And of course I'm talking Windows. Connect your Arduino to a USB port, and then Windows will ask you for the driver. Point Windows to the driver that's in the driver's folder in that structure, that folder structure that you copied to the programs folder. There's a driver folder, and it's the driver for your Arduino is in there. And then you're done. Well, not quite. Now you need to run the Arduino IED, which is the Arduino EXE, and this will create the Arduino folder in My Documents, and that's where all your code is going to go. Now you need to create a folder called Libraries, and it is case sensitive, it's lowercase l, and you need to create that in that Arduino folder that the Arduino environment just created. Don't know why it doesn't create that. The newer versions might. I use 1.0. The newer version, maybe it creates that. But 1.0 did not. And that's where all the libraries go that you add. It comes with a lot of our libraries already installed, but those are in the program folder. The ones that you download and add on or create yourself will go in that libraries folder. Okay. So what you'll end up with under My Documents is an Arduino folder that the Arduino IED will create for you, and then you'll create that libraries folder. And your code goes in the folder, in folders underneath Arduino. You don't put your code directly in the Arduino folder. You'll create a folder with your project name, and that project name needs to have no spaces, can't start with a number. So you need a very almost DOS friendly name for your Arduino application folder, and then in that folder that's where your code will go. And like I said, the libraries that you write or install go in the libraries folder. Okay, now once you open the IED, you have to, there's two subroutines you have to have. One is the setup routine, and this is where your setup code goes. Things like telling the Arduino whether a port is going to be a digital port or an analog port, or whether it's going to be an input or an output. And that's also where you might initialize objects and libraries, like for example doing serial communication. You need to initialize the serial object and set the baud rate. And then the other subroutine that you must have is the loop, and this is where your main code that you want to go. This loop runs repeatedly. Every cycle this runs. You must have these functions. This is the bare minimum. Okay. These two functions, before these two functions is where you would put your library includes and your global variables. And after those two functions is where you would put your own functions. Okay, now I'm going to do a simple line follower example. And we're going to use the Arduino Mega. We're going to use the Pololu QIK motor controller, which controls small motors using serial. And we're going to use a line sensor. to sense the line. Okay, so our code, we would want to do an include for the motor controller, because Pololu was nice enough to publish a library that allows you to easily control your motor controller. And we're going to do an include for the library that Pololu has written for the line sensor. And if we go to the Arduino.cc webpage, there's a whole load of useful libraries there, and we're going to download and reference the PID library. Okay, I'm going to put those at the very beginning of our code, and then we're going to create our global variables. The first of which is the set point and the input and the output. And these are going to be global variables that we use in our PID routine, which is how we're going to actually follow the line. And this is our object from the library. This is a PID object, which we're going to name myPID. And here you can see those global variables, the input variable, the output variable, and the set point variable. And you can see there's an ampersand in front of them, and that's sort of a C++ism that allows us to directly access those memory locations. When we call those, when we set those variables, we will set them globally. The 5, 0, and 2 are the initial P, I, and D parameters. And okay, so that goes there, and we also need to define some global constants. Number of sensors, 8. Timeout for looking at the sensor is 2500, I believe that's microseconds. And the emitter pin, which is the pin that turns the sensor on and off, is going to be digital pin 52. And now here we're going to create the object for the line sensor. And the first parameter is a unsigned car array, and that is the array where we're going to store the pin numbers for each of the sensors, 37 through 51. And then we have our constants, the number of sensors, the timeout, and the emitter pin. Okay, and now we're going to create the motor controller object, and those parameters are the pins for the motor controller, for the motors. Well, 0 and 1 are the serial port. Okay, and we're going to set a global variable for the speed. Okay, now our setup routine, we're going to do a serial begin. This initializes the serial library and sets it to a baud rate of 115K. And then we're going to initialize our global variable called setPoint, and this is for the PID routine, and the setPoint is the value where we want the PID to try to attain from the line sensor. In other words, when we're at 3500, the line is in the center of the sensor. And then we want to turn the PID on, so we're going to call setModeAutomatic, which is just turns PID on, and we're going to initialize the motor object. And now here's our main loop, where we are going to call the line sensor object to get the position. We're going to load the position of the line at the beginning of each iteration into the position variable, and then we're going to load that position into the global variable input. And since that used that ampersand, that means as soon as we do that, the PID routine sees it. We don't have to call the PID routine to get it to use that input. But we do need to call compute. We need to call a method on that PID routine, the PID object, to compute the output value of the PID routine. And then we need to use that output value to control the motors. So now we're going to call the motor object and set the speed of each motor, and we're going to offset the speed given the output coming from the PID routine. And then we have a delay of 20, which is 20 milliseconds, which makes this loop run 50 times per second. And that's all we really need. Of course, we could add a whole lot more things to this program, but this is the basics. For example, we could put a button on the robot that allowed it to start and stop. The way it is now, you basically have to turn the robot on and it will immediately start following a line, and you have to grab the robot and turn it off to get it to stop following the line. Another thing you might want to do is you might want to have some sort of a lap counter so that the robot knows how many laps it's gone. It could even time itself and store how many seconds it's getting per lap. You could do some sort of auto-tuning for the PID routine. There's actually an entire library for that on the Arduino page. Lots of things we could add. But this is the basics, and I really wasn't trying to teach C++ programming here. I was just trying to give people a feel for what it's like to program inside the environment, and the power of using libraries with the Arduino. That's really one of Arduino's biggest selling points, is that there's a huge community out there, which means tons and tons of libraries out there. If you go to any electronics website and you see an electrical component, an integrated circuit, there's probably already a library written for that. Type the part number for that into Google and type Arduino and type library, and you will find a library for that digital component. So now I want you to get out there and build a robot. This happens to be my robot that I entered in the robot rally. Anyway, good robot building. Thanks for watching.